All right, why don't we start? So welcome everyone to the Oxford Lectures on the Philosophy of Mathematics. I'm Joel David Hempkins, and this is the third lecture. And the topic today is infinity. And I would like to start by telling you the parable of Hilbert's Grand Hotel. Here's the hotel. It has infinitely many rooms, floors, one room per floor. There's gigantic suites, very, very nice. And at the moment, it's completely full of guests. There's a guest in every single room. And the manager sees a new guest coming. So here's the new guest. And the manager would like to accommodate this new guest into the hotel. And what is he to do? Well, it's rather clear what the manager should do. All he's going to do is direct the person that's currently in room N to move to room N plus one. So everyone is going to move up one room. There's no top room or anything. The rooms go like the natural numbers. So for every room, there's one above it. So everyone can move to the next room higher. And after that process happens, then of course the bottom room will be empty and the new guest can go into room 0. So in this way, even though the hotel was completely full, the manager can accommodate a new guest. All the guests, of course, when they checked in, they had signed an agreement saying that they agreed to follow the manager's instructions. If he needed to move people around for whatever reason to accommodate new guests, then they were obliged to do that. Okay. So the next day, another guest came, and of course he could just do the same thing again, yes? And the following day, maybe 1,000 guests came all at once. And so in that case, we can just we can just move the occupant of room N to N plus 1,000, right? Move everyone up 1,000 rooms, and then guest I will go to room I. So if the guests are numbered from 0 to 999, then they can fit into their room. So we can make 1,000 rooms free by having everyone move up 1,000 rooms. Okay. So that strategy works very well, even when the hotel is completely full. We can still accommodate new guests. But the next weekend, a bus arrived. Let me just. It was Hilbert's bus, Hilbert Bus Company. Okay, and it had infinitely many seats in it. Okay, I'm just going to draw some of them. Okay, here's seat 0, seat 1, seat 2, seat 3, seat 4, 5, and so on. Now, infinitely many people on that bus, and everybody on the bus wanted to get into the hotel. And so now the previous strategy won't work because we can't move people up infinitely many rooms because every room number is some finite number. We could have moved them up 1,000 rooms and so on, but we can't move them up infinitely because they each need to go into a specific room. And so the question is, what should the manager do? If you have a suggestion, just type it in the chat. And so the manager would like to accommodate all of these people. So we need to say, where should the person in room N go? And then where should the person in seat S go? Which room should they go in? And so I want to fill in these blanks so that every guest gets their own room. We're not going to double up people or anything like that. And so let's see. Okay, so send everyone to 2n. Okay, it says 2n factorial, and I'm not sure if you really mean 2n factorial or 2n with an exclamation, that you're emphatic about it. Okay. So we have some suggestions that we should send room N to room 2n. Okay, that's a good idea because these are all different rooms. If the n's are different, then 2n's will be different. And now the thing to notice about that situation is that these numbers are all even. And so therefore, after we send the current guest in room N to room 2n, then it frees up all of the odd numbered rooms. So now the question is, where do we put the person in CS? It should be an odd number because these even numbered rooms are all fully occupied. And so where should we put the person in CS? Has anyone suggested in the chat? let's see. Oh, we have 2s minus 1. So I started with seat 0, though, so I don't think you mean 2s minus 1, but 2s plus 1, I think, works just great. So the first odd room will be 1, and when s is 0, then that person is going to go to room 1 and 3, and so on the next one. Okay, so these numbers are definitely odd, and they're all different if the seat is different, and so we found a way of giving everyone their own room. All the current guests get the even rooms, and the bus passengers get the odd numbered rooms. Okay, so we were able to accommodate everyone. Now, the next weekend, another group of passengers arrived, and it was this time, well, it was Hilbert's train, and it had a lot of cars on it. I'm only going to draw some of the train cars. Okay, it keeps going. So that's Hilbert's train, and each train. So this is car 0, and this is car 1, and car 2, and so on, car 3. And then each train car has infinitely many seats: 1, 0, 1, 2, 3, and so on. And this train car also has infinitely many seats: 0, 1, 2, 3, and so on. And so we have infinitely many train cars, and each of the train cars has infinitely many seats. And so the manager, and they all want to get into the hotel, the manager needs to decide what to do. So we need to send the current room occupant of room N to some other room, and then we need to send car C, seat S, to some room number. And the question is, how can we do it? So if someone could make a suggestion in the chat. Okay, so, well, I can get started here, I suppose. The hotel is maybe completely full already, but we can free up a lot of space by sending room N to 2N, just like we did before. So that will put all the current guests into the even numbered rooms only, so we'll have all the odd numbered rooms free. And so all I need to do is come up with an odd number that's depending on the car number and the seat number in such a way that I'm not putting 2 people into the same room. So do we have a suggestion here? So I think there's asterisks there. I'm going to interpret that as exponentiation in the chat. And so the suggestion is 3 to the C times 5 to the S. So this is definitely an odd number because it's a product of power of an odd number times another odd number. So it's definitely odd. And furthermore, if I change this, different car numbers and seat numbers will never give the same value for this because of the uniqueness of the prime factorization, right? This is the prime, 3 and 5 are prime. And so every number of this form can be decomposed uniquely into this form. And therefore, I've given a different room number to every train passenger, no matter which car or seat they came from. Okay, very good. So, so we were able to fit the entire train into Hilbert's Hotel. So, okay, so what is this parable really about? It's about the concept of countable sets. So a set is countable when it fits into Hilbert's Hotel. So in other words, if we think of Hilbert's Hotel, the room numbers are just like the natural numbers. And so a set is countable when it can be placed into one-to-one correspondence with a subset of the natural numbers. Another way to think about countability is a set is countable when you can list off the elements, when you can make a list from the elements. So, so the typical countable set, we can enumerate the elements by simply listing them off. I mean, if there are any, the empty set is also countable because it's bijected with the empty subset of the natural numbers. If a non-empty countable set can be enumerated like this. Okay, so the the arguments we gave for Hilbert's Hotel really show a number of things, namely the union of 2 countable sets is still countable because we had the original hotel occupants and we had the bus, and we were able to put those together into and make them bijective, the union bijective with the rooms of Hilbert's Hotel, in other words, with a set of natural numbers. So the union of 2 countably infinite sets is still countably infinite. And the train argument shows that the union of countably many countably infinite sets is also still only countably infinite. And I want to give a number of different arguments for that result. So let's think a little bit. So let's erase the hotel. And if I think about, say, the natural number lattice, so I think of it as like this grid, okay, and then horizontally here, okay. So if these are labeled 0, 1, 2, 3, 4, and so on, 0, 1, 2, 3, 4, then I'm thinking of these grid points. They each have an x coordinate and a y coordinate, which is an integer. So those grid points are a picture of n cross n, the set of pairs of natural numbers. You know, and so maybe I have some point, say n comma k here. And what I claim is that the number of pairs of natural numbers is equinumerous with, can be put into bijective correspondence with the natural numbers themselves. Okay, I'm claiming the set of pairs of natural numbers is equinumerous with the natural numbers. And one easy way to see this is we think about this grid, and then we just start at the origin here, and I'm just going to describe a certain winding path. Namely, I kind of zigzag back and forth like this, and I just follow this zigzag path. Okay, and then I look at the order in which the points were visited on that path, and the point is that that gives me a way of numbering the nodes in the grid. For example, this will be the 0th one, and then 1, 2, 3, 4, 5, 6, 7, 8, and so on. So I've just defined a one-to-one correspondence between the grid points and the natural numbers, namely the order in which they appear on that winding path. Every point in the grid will be visited by that path eventually if I wait long enough. And so that shows that the number of grid points, the number of pairs of natural numbers, is equinumerous with the number of natural numbers. There's a slightly better version of this argument that Cantor had come up with. So let me erase this one and we'll do it again. If we just organize the argument a little bit differently, okay. So here's the grid again. So this is the natural number grid, n cross n. And now all I want to do is I'm going to start here, and then I'm going to visit them in this order. I always go up and to the left, okay, like this, okay. And so this would be 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on as I go up. So instead of going back and forth, I only go up. So when I get to the end here, I zip back to the lower right and go on the next diagonal. And when you do it that way, it turns out that if you think about point x comma y here in the grid, where x and y are integers, if I think about how I got there, well, I had these earlier lines. So there's 1 point on this line and 2 points on this one and 3 points on this line and so on. And so if I count the number of points that were before this point, I'm going to get 1 plus 2 plus 3 and so on, plus, and then of course these lines have the property that x plus y is constant. And if you think about the number of points, then the last one is going to be x plus y. That's the number of points on the previous full line. And then the number of points earlier than this point on its own line is just y. And the point is that this sum we can calculate with a closed form polynomial expression, namely it's 1/2 x plus y times x plus y plus 1 and plus y. So this is a polynomial function, p of xy. If I let p of xy be this polynomial expression, then this is a bijection between the natural number, between the pairs of natural numbers and the natural numbers themselves. So there's a polynomial bijection between n cross n and n. It's an open question whether there is such a polynomial bijection between q cross q and q if we go to the rationals. There's a really interesting math overflow question about that if you take a look there. Okay, so we've used this word equinumerosity, and of course we talked about this in the first lecture also, namely two sets are equinumerous if there's a one-to-one correspondence between those sets. If I can associate each point in one of the sets with a point in the other set in such a way that different points get associated with different points, and every point in either set has a partner. So that's a one-to-one correspondence. It's a way of seeing that the two sets have the same size. So when I look out, say, on a classroom full of people, then I can tell that the number of people in the class is the same as the number of noses in the class, because I can make a one-to-one correspondence between the people and their own nose. That's an association. So I don't have to count the number of people and then count the number of noses in order to know that those two numbers are the same. I just observe that everybody has a nose and there aren't any extra noses and no one's got noses in their pocket or something like that. And so it's a one-to-one correspondence between the set of people and the set of noses in the room, and therefore those two sets have the same size, even if I don't know what that size is. Okay, I want to mention Galileo's treatment of the Cantor-Hume principle. So the Cantor-Hume principle, remember, was the principle that said two sets have the same number of elements just in case they're equinumerous. And Galileo wrote on this well before Hume about some confusing aspects of it in his dialogues concerning two new sciences in 1638. So the dialogue was between these two characters, Simplicio and Salviati. And what Galileo observed is he considered the natural numbers 0, 1, 2, 3, 4, and so on, and the squares of the natural numbers. So the numbers, well, 0 squared is 0, and 1 squared is 1, and then 2 squared 4, 9, 16, 25, and so on. Those are the perfect squares. And what he noticed was that on the one hand, it seems like there's many fewer square numbers because there's all those gaps in between. There's numbers that aren't squares and big holes in between the squares. So most numbers aren't squares. So it seems in some sense that there are many fewer squares than there are natural numbers. But on the other hand, we can make the one-to-one correspondence. We can associate every number n with its square. So associate n with n squared, and that's a one-to-one correspondence between all the numbers and all the perfect squares. And so in that sense, those two sets have the same size, and Galileo found that extremely frustrating. And it wasn't just that case. He had some other cases. So his characters considered, for example, two line segments. So if we have, say, one line segment like this, and then another line segment like this, a longer one, then we can make a one-to-one correspondence between the points on this line and the points on this line. Namely, we just imagine this kind of fan-shaped correspondence. So every point on this line gets associated with a corresponding point on the other line, and it's a one-to-one correspondence. So if I have two different points, then when I apply that fanning out, that sort of stretching, then I'm going to get two different points down here, and everyone has a partner and so on. So this shows then that there's an equinumerosity between the points on this short line and the points on this longer line. And then he went one more. He observed that, well, we can even make an association, say, between, let me consider just the open segment this time. Let me draw it a little bit over here, so I have room. And the infinite line. So, and the way that his association goes is, well, we kind of bend this, this line segment into a semicircle, so a half circle here. And if that's the center of the circle, and then for any point on it, we consider the point that you would get by tracing a ray from the center of that circle to get a corresponding point here. So this point is associated with this point, and this point over here, I draw the ray, is associated with this point, okay? And so every point on the line segment, on the finite line segment, is going to get associated with a point on the line, and even if we go way out here, right, we're still going to have come from some point here. And so this provides an equinumerosity between the finite line segment and the infinite line. Okay. And so he concluded, really, Galileo concluded through his character Salviati, that comparisons of size simply do not apply in the infinite realm. What he wrote is, so far as I can see, we can only infer that the totality of all numbers is infinite, that the number of squares is infinite, and that the number of their roots is infinite. Neither is the number of squares less than the totality of all numbers, nor the latter greater than the former. And finally, the attributes equal, greater, and less are not applicable to infinite, but only to finite quantities. When therefore Simplicio introduces several lines of different lengths and asks me how it is possible that the longer ones do not contain more points than the shorter, I answer him that one line does not contain more or less or just as many points as another, but that each line contains an infinite number. So he's explicitly denying the possibility of size comparisons amongst infinite sets, which is something that Cantor didn't do, right? Cantor is explicitly allowing these size comparisons and giving us a rather robust theory of how these comparisons are to be made. Okay, let's go back to Hilbert's Hotel, because the following weekend, Hilbert's half marathon arrived. So a big race in town with a lot of runners, and they all have a number on their chest, you know, getting ready for the race. And the number on their chest is a rational number, a fraction. Everybody's got a fraction, and none of them are repeated. And the question is, can we accommodate the entire marathon into Hilbert's Hotel using even the current guess? So let's just do that one quickly. Oh, it's too bad I erased the hotel. Okay, let's imagine the hotel is still there. Here it is. Okay, so we want to send room N to something, and we want to send runner P over Q to something where this is a fraction. So can someone make a suggestion? So let's see. Yes, anyone make a suggestion? How are we going to accommodate the whole race into the hotel? Any ideas? Okay, so there's a suggestion. Okay, so that's very good. So we can do basically the same trick as before, because a fraction, of course, even though we imagine the rational line is completely dense with points, every rational number is just coming from two numbers. So the solution for the rational numbers can be basically identical to the solution that we use for the train, which also the passengers have two numbers. So we can send room N to 2N, and we can send runner P over Q to 3 to the P times 5 to the Q. And so the fact that the rationals have this dense order is maybe just a confounding confusion, but actually doesn't prevent a simple analysis that's identical to our analysis of handling the train. Okay, so now the next weekend, it's a port city, and a ship came in. Okay, a big cruise ship. It's not Hilbert's cruise ship though; it's Cantor's cruise ship. The Cantor cruise ship, and it has infinitely many passengers on it. And in fact, every passenger has a ticket, and the ticket has a serial number on it, and that serial number is a real number. So there's the passenger square root of 2, and a passenger whose ticket is the number E, and pi, and so on. For every real number, we have a passenger with that real number. Maybe the integers are maybe in first class, and then maybe the algebraic numbers are in second class, and then there's this mass of transcendental numbers, right? But we have a passenger for every real number, and the question is, can we fit the passengers of Cantor's cruise ship into Hilbert's Hotel? And the remarkable answer that Cantor came up with is no, we cannot do that. The real numbers are uncountable. They cannot be put into one-to-one correspondence with the natural numbers. And so I want to give you a number of proofs of that. Okay, so the remarkable claim is that the real numbers are an uncountable infinity. They are a larger infinity than the infinity of the natural numbers. And so the way Cantor proved this is, well, suppose toward contradiction that they were countable. I mean, we're trying to prove they're not countable. So suppose that they were countable. But that would mean we could put the real numbers on a list, because that's what it means to be uncountable. So if if we could put the real numbers on a list, it would be R0, or let's start with 1 instead of 0, R2, R3, and so on, R4. Okay. And that this is a list containing all the real numbers. Okay, that's the supposition, that we've put the set of all the real numbers into one-to-one correspondence with a set of natural numbers. So I can assume that I'm listing it out. Okay, and now I'm going to define a certain real number. I'm going to call it Z, and I'm going to specify its say decimal expansion. 0.D1, D2, D3, D4, and so on. Okay, these are the digits of the real number that I'm defining, and I just make sure that so each digit D sub n is different from the nth digit of the nth number R sub n. And for specificity, let's say that we always take dn to be either 1 or 7, okay? Just to make it different from the nth digit of the nth number on the list. And now the point of Cantor's argument is that we've got a real number here, we've defined the real number, and the point is that it cannot be that Z is equal to one of these numbers precisely because it's different from Rn in the nth digit. So the nth digit of my number Z is different from the nth digit of this number. So therefore, Z is not equal to Rn for any n. And therefore, this wasn't all the real numbers because I found a real number that's not on this. Okay, so this is basically how Cantor's argument goes. Let me illustrate it maybe with some specific numbers. So let's, I'm going to highlight a certain part of the argument. So let's just suppose, for example, that the first number on the list was, say, R1, maybe it was pi, which is 3.14159.265 and so on. Okay, and then suppose the next number on the list was, what have I got here? E. So what is that? 2.718281828 and so on. Okay, it doesn't repeat after that though. And then suppose we have R3 is say the square root of 2, which is 1.414213 something or other. Okay, and then suppose we have say log 2, R4, natural log of 2. So that's 0.69. What is it? 69? 693.147. 693.147. Okay. And so on. Maybe we have square root of 29, which is 5.385164.8, and so on. Okay. So now the construction of Z is looking at the nth digit of the nth number. So the first digit of R1 is this one, and the second digit of R2 is this one, and the third digit of R3 is this one, the fourth digit of R4 is this one, the fifth digit, 1, 2, 3, 4, 5, this one, and so on. And if you look, those things that I've just circled are lying on the diagonal, and that's why this argument is known as the diagonal argument. This is the diagonal argument, Cantor's diagonal method. We can look at those digits. And so if this was the list that we had been given, then the real number Z that we would produce, and so for specificity, let's suppose that we always use the digit 1 if it's available. In other ways, we use the digit 7 so as to be different. So therefore, this digit was 1. So my diagonal real is going to start with 0.7 because that's a 1, and this one is also a 1, so I should use 7 again. But now this is a 4, so I can use a 1, and this is a 1, so I should use 7, and this is a 6, so I should use a 1. So I'm always using 1 if I can, unless the nth digit of the nth number was 1, in which case I switch to 7. Okay. So for this particular list, this is the diagonal real, and now it's easy to see that this number is different from R1 because look, this one starts with a 7 and this one has a 1. And this number is different from R2 because look, this one has a 7 here and this one has a 1, and so on. So the nth digit of the diagonal real is different from the nth digit of the nth number. Okay, so now there's this subtle, this annoying subtle issue that actually can be seen as completely moot, but I want to mention it, and that is some real numbers don't have a unique decimal representation. I'm talking about the nth digit of the nth number, but of course, real numbers can have two representations. For example, 1.00000 is the same thing as 0.999999. Those two real numbers are both the same, they're equal. And so that real number one has two different decimal representations. Okay. But now the only phenomena, the only real numbers that have more than one decimal representation are the numbers that either end in all nines or all zeros in their decimal expansion. And my number definitely doesn't, because I don't have any nines at all, and I don't have any zeros. I was always using 1 and 7. So therefore, if you have a real number that happen to have two different representations, then it's definitely not equal to my real, because my real, the diagonal real here, has only one representation because it has only 1s and 7s in it. And so I didn't have to do anything special at the nth stage to make sure that it was different. So that's a sense in which that non-uniqueness of the representations is moot. I mean, there's another way to argue, namely that because I'm using 1 and 7, I mean, if a number didn't have unique representation, then I can either pick 1 or 7, and one of those is going to be different from both of the representations. So you can argue that way as well. Okay, so now this diagonal argument is, of course, an extremely common way of describing Cantor's argument, but it's a little bit different from Cantor's original argument. So I want to describe Cantor's original proof that he gave much earlier. So let's do that. So we want to show that the set of real numbers is uncountable. So we suppose it is countable. So that means we can put it on the list. So R0, R1, R2, R3, and so on. Okay. And now we're going to consider the real number line. And we're going to specify a certain nested sequence of intervals. Okay. So maybe I look at where R0 is, maybe it's here. And what I do is I pick an interval, sort of A0, B0, that excludes R0. Okay, I pick my interval so that R0 is not inside of it. And now I look at the next one, R1. You know, maybe it's here, R1. And so what I do is, this is the current interval. I'm going to shrink the interval to make it smaller, A1, B1, so as to exclude R1. I shrink the interval to exclude the next point. And then, okay, I look at the next point, R2. Maybe R2 is over here. Maybe I've already excluded it, in which case I don't have to do anything. I can keep the same. I can keep A2 and B2 to be the same if I've already excluded it, you know. But then maybe R3 is inside, so I should shrink again. So here I'm going to shrink A3, B3, and so on. So in this way, I make this nested sequence of closed intervals so that the nth interval excluded the nth point on the list. Okay. And now it's a general fact that whenever you have a nested sequence of closed intervals, then there's a point that's inside all of them, namely the supremum of the A's. The A's are increasing or non-decreasing here. So I can just let Z be the sup on n of the ANs. So this is a bounded, it's a monotone sequence there. So the supremum will exist here. They're all bounded by the B's. And Z is in all the intervals. And therefore, it's not equal to any one of these reals because all of these reals were thrown out of the intervals at some stage. Okay, so that's a bit closer to Cantor's original argument. And sometimes one sees mathematicians making a lot of fuss about the difference between these arguments, that this was the original argument and the diagonal argument didn't come until later. But I think this fuss is wrong. In my view, this is just a mere presentational difference. And the reason is that to specify successive digits of a real number is the same thing as fixing an interval. You know, the set of all real numbers whose first digit is, say, 0 point something, those are exactly the real numbers in the unit interval. And if I say, well, I'm thinking of a real number and it's 0.1 something, then that's specifying a certain subinterval of the unit interval. And if I say, well, no, it's really starting 0.17 something, then that's specifying a further closed interval. So to specify successive digits is exactly to specify a sequence of closed intervals. And therefore, there's a sense in which these arguments are identical. They're undertaking the same construction, and it's maybe the diagonal argument is a little easier to see exactly how it's working and which interval you're picking exactly, whereas originally it didn't really matter which interval as long as you exclude the nth point. Okay, so right. So I'd like to talk about transcendental numbers. So, right. So in the real numbers, we can consider, say, an algebraic number like square root of 2. That's a number that solves a polynomial equation over the integers. So the square root of 2 is the solution of x squared minus 2 equals 0, because x squared equals 2, right? So x squared minus 2 equals 0. So that's a polynomial with one variable over the integers, and the square root of 2 is one of the solutions of that, one of the roots. That's what it means to be algebraic in the real numbers. And if you're not algebraic, then you're transcendental. And it was an open question for a long time whether there are any transcendental numbers, or is every real number solving some equation. And this was first solved by Louisville in 1844. And Louisville presented a specific number. It's now known as the Louisville constant. So it's the number, it's basically 0.11000. Oh, let's see, I'm probably have the wrong number of zeros here. Okay, and I think I don't have enough zeros there. But the point is that the Louisville constant is what's called a lacunic number, because it has these lakes of zeros, and those lakes become enormous. He uses the n factorial. So we have a 1 in every n factorial digit place, and all the rest are zeros. So these ones get further and further spaced apart. And then one can argue that such a lacunic number is going to be transcendental, because when you multiply that number by itself or squared or added to itself, then if you go out to a far enough place, those ones don't interfere constructively or destructively with each other in that arithmetic, and therefore there's no way to make them all cancel out to make 0 in the polynomial. So that's basically why the Louisville constant is transcendental. But now it also follows from Cantor's theorem that there are transcendental numbers. Namely, Cantor proved that there's only countably many finite sequences of integers. And if we interpret such a sequence of integers as a polynomial, therefore there's only countably many polynomials over the integers. And each such polynomial has only finitely many solutions. So I can specify any algebraic number by listing the polynomial that it's a solution of and its place amongst the zeros of that polynomial. And therefore, there are only countably many algebraic numbers, but there are uncountably many real numbers, and therefore there must be some real numbers that are not algebraic. In other words, there are transcendental numbers. So Cantor's proof really shows more that there are most real numbers are transcendental, because there are only countably many, in other words, very few algebraic real numbers. Therefore, most real numbers are transcendental. Now, there's an aspect of this argument I want to highlight, having to do with whether it's constructive or not. So an argument is constructive in its informal sense. There's a technical sense of constructive, about constructive logic and intuitionism that we're going to talk about in week 6. But for now, I'm just talking about the sort of common informal notion of whether a proof is constructive or not. And the question is, does it exhibit it's asserting that there's a certain kind of number, a transcendental number, and the question is, does it exhibit a specific number that's definitely transcendental? So that if so, it would be a constructive proof. And a non-constructive proof is one that just proves, say, a pure existence claim without giving you an example of it. So, for example, consider the following argument. There must be a cat in this warehouse because we don't see any mice. So that's a non-constructive argument because it's finding sort of indirect evidence for the existence of the cat, and it's not exhibiting the cat. So a constructive proof that there's a cat in the warehouse would give you the cat. It would show you the cat. You would be able to tell a lot more information about the cat, like what its markings were and whether it was friendly or not, and so on. So many mathematicians prefer constructive proofs because we tend to get more information from them. But there's another sense in that oftentimes there are non-constructive, very soft proofs that just prove the existence claim, and that to actually exhibit the thing is often more finicky and messy, and not necessarily better than. Okay. So the question is Cantor's proof of the existence of transcendental numbers constructive or not? And it's extremely common to find mathematicians claiming that it's not constructive. The way I just described it, it wasn't constructive. I said, well, there's countably many algebraic numbers, so therefore, since there's uncountably many real numbers, there must be some real numbers that are not algebraic. That's basically a non-constructive version of the argument. But if we reformulate the argument even slightly, then we can make a constructive version of it. Namely, Cantor doesn't just prove that there's countably many algebraic numbers. He tells us exactly how to list them. We can list off the finite tuples of integers, and we can list off the, the roots of those polynomials and so on. So we can, we can have a definite procedure for enumerating the countably many algebraic numbers. And furthermore, the diagonal method is also constructive. For any list of numbers, the diagonal method produces a specific number that's not on the list. And therefore, given the list we constructed of all the algebraic numbers, if we undertake the diagonalization procedure, we will end up with a specific real number that is not on that list. In other words, that it's not algebraic. And so this would be a constructive proof using Cantor's diagonalization of the existence of transcendental numbers. Okay, now I want to talk about Cantor's generalization of his uncountability argument to the number of subsets of a given set. So the claim is that every set has more subsets than elements. So the power, in other words, X is always strictly smaller than the power set of X. So this is the set of all subsets of X, okay, the power set. So suppose that X was equinumerous with the power set of X. Okay, so that would mean that we would have a listing. So of all of the subsets of X, we could have a one-to-one correspondence between an element A and a subset X sub A, a subset of X. We could associate every subset with an element in a one-to-one correspondence. I suppose towards contradiction that we could have such an association. And now the argument is let D be the set of A such that A is not an element of X sub A. So in other words, the set of elements of X that are not members of the set that's named after them. Now it follows that this set D, well, it's a subset of X. And since this was a one-to-one correspondence between the elements of X and all the subsets of X, this set would have to be one of these X sub A's. But notice that A is in D if and only if A is not in X sub A. That's the definition of D. So therefore, D is definitely not X sub A for any A. Okay, so therefore, we get a contradiction. This set couldn't have been one of the X sub A's because it disagrees with X sub A about whether A is an element. So what this shows is that the power set of a set is bigger than a set for any set. And that tells you immediately that there must be lots of different sizes of infinity, because we can start with the natural numbers, and the power set of the natural numbers is a bigger infinity by this argument. And then the power set of that set is a bigger infinity than that set. and the power set of that, and so on. So there must be infinitely many different infinities by this argument, because we can always just keep applying the power set. And in fact, it goes even more than that. So the number of infinities, there are more infinities than any given set, because if I can associate to each set a different infinity, then if I pick a set of that size for each element of the set and take the union of all those sets and then say the power set of that, then I've got a set that's bigger than any of those infinities. So therefore the number of different infinities, well, it's wrong to talk about the number of different infinities because it's more than any given set. So there are more different sizes of infinity than there are elements of any given set by that argument. Okay. So we have a question here. Let's see. Right. About whether Cantor's proof is constructive in the sense of constructive logic, and the answer is yes. It's constructive in that sense. You can undertake Cantor diagonalization. So Russell wrote shortly after Cantor about the number of propositions, and he used Cantor's reasoning to argue that there are more propositional functions than there are objects. And it was basically the same as Cantor's, as this proof of Cantor's. Also, of course, the logic is identical in what's known as the Russell paradox, which we're going to talk about in week 8. That's basically a claim that there are more classes of objects than there are objects. So another way to describe the argument is that suppose you have a set of people and you're going to form committees. All possible committees, the universal committee where everyone's a member, the empty committee, there's all the one-person committees and all the two-person committees and so on. So we can consider how many possible committees can you make with a set of people, even if you had, say, infinitely many people. And the answer is that there are more possible committees than there are people always for any set, even an infinite set. And the proof is just the argument that we give here. If we could associate every committee and name it after a different person, then you could form a committee of all people who are not on the committee that's named after them. And that would be a committee that can't be named after anyone, because that person would be on the committee if and only if they're not, by the Cantor argument that we just gave. Last year, one of my students, Martha Story, considered the number of fruit salads that you can make from a given assortment of fruit. And of course, you can prove using Cantor's reasoning that you can always make more possible fruit salads than there are pieces of fruit, because you're really talking about the subset of the fruits that you put into the fruit salad. Okay, well, Russell had a funny story about the diary of Tristram Shandy that I'd like to mention that. So what he wrote was, Tristram Shandy, I'm probably mispronouncing it, as we know, took 2 years writing the history of the first 2 days of his life, and lamented that at this rate, material would accumulate faster than he could deal with it, and so he could never come to an end. Now, I maintain Russell's writing. If he had lived forever and not wearied of his task, then even if his life had continued as eventfully as it began, no part of his biography would have remained unwritten. So the point is that Tristram Shandy is, of course, famous for his very elaborate diaries, and Russell is saying, well, even if he spent a year writing about every day, then if he lived long enough, then he could write about the nth day during the nth year, and he could continue that forever. So there's a sort of bijective correspondence between the days and the years in a series of eternal time. This is related maybe to the cartographer's paradox. So Borjas wrote about this. So let me just read it to you. In that empire, the art of cartography attained such perfection that the map of a single province occupied the entirety of a city, and the map of the empire the entirety of a province. In time, those unconscionable maps no longer satisfied, and the cartographers' guild struck a map of the empire whose size was that of the empire, and which coincided point for point with it. The following generations, who were not so fond of the study of cartography as their forebears had been, saw that this vast map was useless, and not without some pitilessness was it that they delivered it up into the inclemencies of sun and winters. In the deserts of the West, still today, there are tattered ruins of that map, inhabited by animals and beggars. Okay, so, but of course one can push this farther and say, well, why not have a map whose scale is larger than 1-to-1? And so what I wrote in response was, I encountered the competing empire across the sea with its own grandiose map at a scale far exceeding 1-to-1, larger than life. So the map of the city fills the province, and the map of the province fills the empire. Each square meter of land is depicted on 1 square kilometer of the map, which displays the cellular structure of plants and the elaborately magnified details of the handwriting in the citizens' notebooks and diaries, written as though with enormous brushstrokes on a vast canvas. Indeed, all the details of the map are themselves geographic features to be writ large again and further off, and therefore writ larger again and still further off, and so on continually. The cartographer's accidental drop of red ink on the vellum becomes recorded, magnified first as a pool, and then a lake, and then an ocean, right? So any detail on the map then is larger later on where it's depicted, and then that is depicted larger later on. This is just like Tristram Shandy. Okay, so there's more kind of puzzles like that. I want to now turn to an issue in philosophy. There's quite a lot of discussion about the Cantor-Hume principle that says two sets have the same number just in case they can be put into one-to-one correspondence. But there's another principle that I feel is needed, and that's a principle that's talking about the size comparison of two sets. We don't want just to know when two numbers are the same. We also want to know about the order of them. When is one set less or equal in size than another? And Cantor gives us an answer to that, namely, a set A is less or equal B in size, just in case there's a one-to-one mapping from A into B. Or in other words, just in case A is equinumerous with a subset of B. And when you introduce this idea, this comparative size principle, then a very interesting question arises, namely, suppose you have two sets and each of them is less or equal the other in size. Okay, so what would that mean? So I have a set here A and another set B, and I know that A is less or equal B in size because I have a correspondence of A with a subset of B, a one-to-one correspondence. But suppose I also know that B is less or equal A in size because I have a one-to-one correspondence between B and a subset of A, you know? Then the question is, does this imply that A is equinumerous with B? You know, because I can't seem to get a bijection between A and B, a one-to-one correspondence between A and B directly from that situation. And the answer to that question is really quite interesting. The answer is yes. And this is a theorem known as the Cantor-Schroeder-Bernstein theorem, the Schroeder-Cantor-Bernstein theorem. And the history is quite interesting because Cantor announced a proof, but he was using the axiom of choice, and it turns out you don't need the axiom of choice. And then there were other proofs announced that subsequently were shown to be wrong. And then finally, okay, we had a sort of contemporary proof. So this is proved in any good set theory textbook, namely the fact that if two sets are less or equal each other in size, then they have the same size. So this is exactly the principle of anti-symmetry for this notion. And my opinion is that we're really not entitled to think that we have a robust concept of size for infinite sets without that theorem. And that's why I find it important to mention this, this comparative size principle and the anti-symmetry of that relation. Okay, let me talk about now another, give a kind of application of that theorem. I guess we're going to go over an hour as we have been a little bit. So Cantor observed very early in 1877 that the real line has the same size as the plane. Now we saw this last week with the space-filling curves, but this was much, much later. Cantor had it already much earlier with this one-to-one correspondence between points on the line and points in the plane. And his argument was just like this. So, so we're going to define a mapping from R cross R to R, namely, if you give me two real numbers, then I want to come up with a single real number Z. And the mapping is, for example, if we have, say, pi 3.14159.265 and so on. And what is the other number? Oh, E. Okay, so 2.718281828 and so on. Okay, then we're going to map it to the real number that we get simply by interleaving the digits. So we're going to map it to 32. So 3, 2, and then 1, 7, 4, 1. Oh my God, let's see, this 4, 1, and then 1. I got confused. Let's see. Okay, it's so 1, 7, 4, 1, 1, 8, 1, 7, 4, 1, 1, 8, and then 5, 2, and so on. Okay, so we just interleave the digits. And the point is that this is the basis of a one-to-one correspondence between pairs of real numbers and individual real numbers. And Cantor wrote to Dedekind in 1877 about this shocking fact that the real line has the same size as the plane, and therefore the same size as space in 3 dimensions or any finite dimension. And he wrote, "I see it, but I don't believe it," to Dedekind, because it was just too shocking to think that somehow this cardinality idea, the equinumerosity idea, didn't track dimension. That all the dimensions of the real spaces in finite dimensions, or even countal dimensions, all have the same cardinality. Okay. I want to mention another issue, and that is, so it's a kind of a feature that I've observed in many cases. So in philosophy, it's very common that we have sort of a partial order relation that we're considering. Maybe we're doing superposition, or we have some grounding relation, or there's some strata with levels that we're considering, and there's sort of underlying order concept for these relations often. And usually there's a choice about whether we consider the reflexive version of the order or the strict version of the order. For example, maybe we have the better than relation in, say, utilitarianism, or the at least as good as relation. So the second one is the reflexive one, and the first one is the strict version. And now I'm calling them order and partial order, but actually they're usually not antisymmetric, because you can have things that are bigger than or equal to each other, but not identical. And so when you drop that antisymmetry axiom from a reflexive order, then you get what's called a pre-order. So it's very common that these fundamental order notions that we're looking at are only pre-orders, they're not partial orders. And when that happens, it turns out that the reflexive version of the order has more information in it than the strict one, because there can be two strict orders that, I'm sorry, there can be, let's see, how do I want to say it? There can be two different reflexive pre-orders that have the same strict order. So therefore, if all you have is the strict order, you don't know which pre-order notion you were using. So therefore, there's a sense in which the reflexive version of the order is the more important one. It has more information, it's more fundamental mathematically, and from it you can define the strict order. And this is exhibited a little bit in, say, Galileo's confusion, because he was finding tension between, say, the Cantor-Hume principle, the idea that equinumerosity tracks size, and Euclid's principle, which is the assertion that the whole is greater than the part, because he felt that a longer line should have more points on it than a shorter line on the basis of Euclid's principle. And so the tension was between Euclid's principle and the Cantor-Hume principle, the equinumerosity principle. But this tension evaporates if you use the reflexive version of Euclid's principle. In other words, if you don't understand Euclid's principle as an assertion about the strict order, but only about the reflexive one, namely that the whole is at least as large as the part, then everything's fine and there's no tension at all. And this phenomenon occurs again and again and again. So you find it, for example, in the literature on infinite utilitarianism that I've written on a little bit. You find people talking about strict versions of the Pareto principle, that if every location is strictly better, then the whole world is strictly better. But really, they should just be saying at least as good in each case, because you can make these Galileo counterexamples and translate them. It's very often the case that Galileo's counterexamples translate into this when you have situations when you're using the strict order. For example, if you have a set and you add a new element, is it larger? Well, it's not necessarily strictly larger. If it was countably infinite and you added a new point, it might only be at least as large. It might be the same size. And that's exactly the kind of situation that comes up again and again. Okay, so let me talk about the continuum hypothesis now. Cantor was intrigued by a very curious observation, namely he identified many different infinite sets. So we have the natural numbers, the integers, the rational numbers, say the set of finite binary sequences, integer polynomials. All of those sets are countably infinite. They're infinite, but they're only countably infinite. They all have the same size. And then he also noticed a bunch of other sets, the real numbers, the complex numbers, the Cantor space of infinite binary sequences, the power set of the natural numbers, the space of continuous functions on the reals, and so on. And it turns out that all of these sets have the same size. They're all size continuum, the size of the real numbers. And Cantor never found an infinite set that was intermediate between the natural numbers and the real numbers. Yeah. And so he formulated the continuum hypothesis. The continuum hypothesis is the assertion that there's no infinity between the natural numbers and the real numbers. And he tried to prove it, and he tried to refute it, and he was never able to do so, and very frustrated by that extremely difficult question. So the question of whether the continuum hypothesis is true or not was the first of Hilbert's famous questions at the beginning of the 20th century that would guide research for the century. And the continuum hypothesis was the #1 question on that list. It wasn't until 1938 that Gödel had proved that if the axioms of set theory are consistent, then they are also consistent with the continuum hypothesis being true, along with the axiom of choice. It was in the same argument. So in other words, Gödel proved that you cannot refute the continuum hypothesis, because if the axioms of consistency, if the axioms of set theory are consistent, then the continuum hypothesis might be true. It's consistent that it's true. And then that was 1938. It wasn't until Paul Cohen in 1963 proved the other side, namely that if the axioms of set theory are consistent, then it's consistent with the axioms to suppose that the continuum hypothesis is false. So this is what it means to say that the continuum hypothesis is independent of the other axioms of set theory. The axioms simply don't prove it, and they don't refute it either way, unless they're inconsistent. We're going to talk much more about that continuum hypothesis in week 8 when I talk about set theory. Okay, so let me talk a little bit more about these different kinds of infinity. So there's these kind of two hierarchies, namely, we have the Aleph hierarchy, which starts with Aleph 0, that's the infinity of the natural numbers, and then the next Aleph is 1, that's the first uncountable cardinality, and that's less than Aleph 2, and Aleph 3, and so on, and these numbers go on forever. So the way that you get from any Aleph to the next one is you just take the next larger size, the next larger infinite size. And then there's what's called the Beth hierarchy. So Beth 0 is the same infinity as Aleph 0, that's the infinity of the natural numbers. And that's less than Beth 1, which is less than Beth 2, less than Beth 3, and so on. And in the Beth hierarchy, what you do is take the power set. Okay, so the Beth hierarchy is defined by iterating the power set. So therefore, Beth 1 is the same size as the real numbers, because that's the same size as the power set of the natural numbers. The real numbers and the power set of the natural numbers are equinumerous. And so therefore, the continuum hypothesis is the assertion that Aleph 1 and Beth 1 are the same. Yes. And of course, this goes transfinitely. So we have Aleph alpha and maybe Beth alpha. And so one may consider, say, the generalized continuum hypothesis, which says that all of them are equal. You know? And this is also known to be independent of the axioms of set theory. It's consistent with the axioms of set theory, and the negation also is consistent. So this cardinal Beth omega, so that's the first limit. That's the first cardinal that's bigger than all the Beths of n cardinals for each n. It's a very interesting cardinal. It's uncountable because it's bigger than all Beth 0. Beth omega, but if you have a set that's smaller than Beth omega, then its power set is also smaller than Beth omega. So it's what's called a strong limit cardinal, because it looks to the smaller sets the same way that all of 0 looks to the smaller sets. That's a strong limit also, because if you have a finite set, its power set is also finite. So a set of size smaller than all of 0, the power set is also size smaller than all of 0. So Beth omega has that property. It's an uncountable cardinal that has some of that feature of all of 0. And this idea of postulating or studying these cardinals up there in the cardinal hierarchy that have the features with respect to the set smaller than them that the smallest infinity has to the finite sets is really a very productive and informative idea in set theory. There's a huge amount of work trying to undertake that, and it leads eventually to what's called the large cardinal hierarchy. I thought I should mention that David Lewis mentioned some of these cardinals specifically. Namely, of course, David Lewis is famous for having an extremely rich ontology with all kinds of possible worlds and possible objects and so on in it. And how many are there? He considered how many possible worlds and how many objects are there and how many properties. And he offered the remarkably precise answers. Beth 2 and Beth 3. There are Beth 2 many objects and Beth 3 many properties. And one can start to see how he's led to these numbers, because if you consider space as modeled by the real numbers, so the locations in space are specified by a real number, or a triple of real numbers or quadruple or whatever, doesn't matter what the dimension is, the number of points would still be just a continuum. So then a region of space would be a subset of the reals, and there are Beth 2 many such things, because Beth 1 is the cardinality of the reals, Beth 2 is the power set. So the Beth 2 answer, you would be led to Beth 2 if you thought that any region was an object, in a sense, any location, possible object. And then if you think there are Beth 2 many objects, then if a property is just any set of objects, namely the collection of objects that have the property, then there would be Beth 3 many properties, because that's just the power set of the number of objects. Okay. So let me close by making sure that we all know how to count. I want to teach everyone how to count in the ordinals. This is something that anyone can learn, even a child. And so let's learn how to count. So let me erase the board. We're going to count up to omega squared in the ordinals. How to count. Okay, so of course, first we count in the natural numbers, and I think you all know how to do that. Namely, we have 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's going to get pretty boring if I keep just writing those numbers. But now, let's imagine that we finished all of that. And then the first number that comes after all of the natural numbers in the ordinals is called omega. So omega is the first infinite ordinal. And it's a limit ordinal. There's nothing that comes right before it, because anything that's before it is a finite number and has its successor, which is also before omega. Okay, so this is the first infinite ordinal, the first limit ordinal. And then when we have this ordinal, then we can keep going. Yeah, that's the thing about the ordinals, is that whenever you're counting, you can just keep going in the same way that you did before. So we have omega plus 1, omega plus 2, omega plus 3, and so on, omega plus 4, and so on. Okay, so for every natural number, we would have omega plus n for that natural number n. Okay, and now what's the first number that comes, what's the first ordinal that comes after all of those ones, after all the numbers of the form omega plus n? for finite number n? And the answer is omega plus omega, which is the same thing as omega times 2. And it's actually, for technical reasons, different from 2 times omega. So ordinal multiplication is not commutative, because this means 2 copies of omega. But if I wrote 2 times omega, then I would mean omega copies of 2. But omega copies of 2 just means 1, 2, 1, 2, 1, 2, 1, 2, and so on. But that, in terms of its order type, is just the same as omega. So we should write it as omega times 2 and not as 2 times omega. So what comes next after this? Well, of course, it's omega times 2 plus 1, and then omega times 2 plus 2, omega times 2 plus 3, and so on. So I can have omega times 2 plus n for any finite number n. And then, what's the first ordinal that comes after all those ordinals? Well, as the n is increasing, then I'm going to run through all of those ordinals. And so I'll get up to omega times 2 plus omega, which is to say omega times 3. That's the next limit ordinal. There's nothing that's right before omega times 3, because anything that's before it is omega times 2 plus n, and then the next number after that would be omega times 2 plus n plus 1, which is still less than omega times 3. Yeah. So then, of course, I have omega times 3 plus 1, omega times 3 plus 2, and so on. And then, of course, we get up to omega times 4, omega times 4 plus 1, omega times 4 plus 2, and so on. And eventually we get up to omega times 5, omega times 5 plus 1, omega times 5 plus 2, and so on. So in general, we're getting all the numbers of the form omega times n plus k, where n and k are natural numbers. Those are the form of the numbers that we counted through. And as n is increasing, then we're getting closer and closer to the first number that's above all numbers of this form. The first ordinal above them will be omega times omega, which is to say omega squared. I want to call attention to something. So that's how you count to omega squared. You count first up to omega, and then basically you count to omega again, but it's omega plus 1, omega plus 2, omega plus 3, and so on. And then after that, we counted to omega again, but now it was omega times 2 plus 1, omega times 2 plus 2, omega times 2 plus 3, and so on. And then after that, we had another copy of omega here with the omega times 3s, and then another one with the omega times 4s, and so on. And so what did we do altogether? Well, we counted up to omega many times. Here we counted up to omega, then we did it again, and then we did it again and again and again. And how many times did we do it all together? Well, we did it omega many times altogether. And so counting to omega squared is just like counting to 100, because when you count to 100, basically you count to 10 times. First you count up to 10, and then in the teens you count to 10 again inside the teens. And then in the 20s you count to 10 again, and so on, in the 30s, and in the 40s, and so on. So to count up to 100, you count it up to 10 times. And furthermore, the numbers less than 100 are exactly the numbers that are represented with 2 digits in base 10. But when we counted up to omega squared, we counted up to omega, and then again and again, omega many times. We counted up to omega many times, just like counting to 100, 10 times. And furthermore, the numbers less than omega squared are exactly the numbers that have a representation in base omega using 2 digits. So please think about counting to omega squared just like you would think about counting to 100. It's really extremely similar. So I guess that's all I had to say today. So we can open it up for discussion if people want to stick around, and I'm happy to chat. If there's questions in the chat, or if people want to unmute and ask. So please go ahead and ask. Let's see.
Hello, Professor Humpkins?
Yes.
Yeah, thank you. In fact, I wrote my question in the chat. And in fact, last week I put part of it.
Oh, I see. Are you Ahmed?
Yes, please.
Right. Okay. So is there a problem between the infinite and the problem of induction? So are you're talking about, say, induction in the sense of Hume or mathematical induction? Which one are you referring to?
In fact, in general.
Okay, I see. So it's very common in mathematics to use this ... And you can see I just put a bunch of ... on the board, and so maybe you're objecting to that. And it's reasonable to object to that. And so the question is, the way I'm interpreting it is, what do we mean by this ... And is that a form of Humean induction that we're supposing that it's just going to continue as it had been? And is there any meaning in that? And I tend to agree that maybe there isn't meaning. Of course, this account here was a largely informal account to build your intuition about what the numbers up to omega squared look like and how do they work. But of course, in mathematics, we can give precise definitions of what it means to have ordinals and to add them and multiply them and their properties. And there's no ... in that discussion at all. And we can prove theorems and so on. So in the use of ... in the formal account is totally absent. And so that's one way of answering your question, is that we're not relying on this vague ... idea. But nevertheless, it's useful for building intuitions about the nature of these objects, and so we use it. There's another sort of more forceful objection that one could make about this ... and that is, say, in the debate on pluralism, which I'm a party to, many mathematicians have the idea that we have some kind of definite understanding of the nature of the natural numbers, and when they talk about what that is, then they say, well, the number 0, 1, 2, 3, and so on. And and it's very difficult to give a fully rigorous account of what this and so on really means. Of course, we have the Dedekind axioms, the categorical account of the natural numbers, namely that any mathematical structure satisfying Dedekind's axioms, any two of them are isomorphic. So in that sense, it's pinning down a unique structure. But if someone is doubting about whether the natural numbers form a coherent, definite mathematical structure, then they're not going to like Dedekind's axioms, because of course the axioms are second order axioms that rely on the concept of an arbitrary set of numbers. The induction axiom says for any set of numbers, if it has 0 and it's closed under successive, then it's everything. But how can it possibly be acceptable to found the definiteness, to establish the definiteness of the natural number concept by using this comparatively murky concept of an arbitrary subset of an infinite collection? And so it seems totally unacceptable to appeal to Dedekind's categoricity result if what you're trying to do is establish the definiteness of the natural number concept. And so if we rule that out, then we're just back at this ... situation, like the question was. And so I wonder, and I've asked this in some essays, whether we really do have such a definite concept of natural number, and maybe we don't. And maybe we should be pluralists about arithmetic for that reason, if they're possibly different. We already understand quite deeply how different models of set theory can have different mathematical structures for the integers inside them, and they're not isomorphic between this model of set theory and that one. So if you're a pluralist about, say, the nature of the set theoretic universe, then it's just a little bit of a step to also be a pluralist about the natural numbers, because we already understand in a quite deep way how it can happen that different models of set theory have different non-isomorphic natural numbers. Okay, I'm not sure if that answered your question, but I gave it a shot.
Thank you very much.
Sure. Okay, so what about other questions here? If someone wants to unmute, go ahead and ask. Oh, okay, so someone's asking about subtle assumptions behind, Teddy's asking subtle assumptions behind the idea that the Aleph numbers are indexed by the ordinals. Okay, so this is exactly right. That's a very important consideration, namely, so according to Cantor is implicitly using what we now call the axiom of choice. I mean, he wasn't working in a formal system, but it turns out that if you have Cantor's conception that the cardinals are linearly ordered, so he had these Aleph numbers indexed by the ordinals, and if that is all the cardinals, then it follows that the axiom of choice is true. In other words, the axiom of choice is equivalent to the assertion that the cardinals are linearly ordered. It's kind of surprising. I mean, of course, if the axiom of choice is true, then you can prove that any two sets are comparable in size, because you can well order both of them, and you can also prove that well orders, any two well orders, one of them is isomorphic to an initial segment of the other. And so that will give you the comparisons of the cardinalities also from the axiom of choice. But the other direction is really a result due to Hartog, namely, so if but for any set, there's a well-ordered cardinality that's not smaller than it. And so if the cardinals are linearly ordered, then the original set would have to be less than that one, and therefore would be well-ordered, and that would give you the axiom of choice. So it's a very interesting question. The possibility of having a linear list of all the infinities, a linearly ordered list, is equivalent to the axiom of choice. So that's the underlying assumption about this Aleph hierarchy, if you really intend it to contain all the cardinals. I mean, another response is, well, I don't want the axiom of choice, but then you can still define the Alephs, but they won't be all the cardinals. There might be some other cardinals that are incomparable with all of these Aleph cardinals. And that's the kind of situation that happens in these models of set theory that don't have the axiom of choice. Okay, let's see. I see. So Aaron says maybe there's some really big numbers are still being created. Okay, so I guess this is related to the question, of course, is mathematics invented or discovered? And so are the numbers already there and we're just finding them, or the infinite cardinalities, we're just finding them? Maybe they already exist, and we're discovering these objects out in the Platonic realm, even if no one had ever counted that high. Maybe they still exist anyways. Or are we creating these numbers? By counting a little bit higher, we create more and more numbers that way, including the infinite ones, right? And so this is a fundamental question related to your remark. Any other questions?
Yeah, I have one more question regarding one of your proofs that you mentioned. So you gave an alternative proof for the uncountability of the reals with these nested intervals that shrink, but always the real number will be caught between the margins.
Yes.
I'm wondering whether there's an assumption in that proof that all the reals can be bounded between an A and a B. Well, not necessarily all the reals, but at least from some rank onwards. So it seemed to me that the proof relied on this assumption that at the outset you can sort of have this A and B that you continuously shrink to leave outside the real number. But it seems to me that they have to capture all the reals from a rank onwards.
No, I think that's not right. So the point is that so we're trying to show the reals are uncountable. So we suppose that they're countable. So we have this list, these R sub n's, of all the real numbers. And of course, those numbers aren't bounded in any interval, because we know already about a lot of real numbers. For any given interval, there's a real number outside. If you just add one to the right endpoint, that's going to be something not in that interval. So the list of real numbers was supposed to be jumping all over the place, right? But the point of the proof is that we can ignore the ones that are really big, because we have this closed interval. And if we've already excluded R sub 2, then we don't need to worry about it. We've already diagonalized against that one. So we're shrinking. The only ones we do have to worry about are the ones that are inside. If it's already outside, we've already shrunk to avoid that one. So there's no problem about the RNs being outside very far away. We're going to just concentrate on this little tiny region. And we could have done it anywhere. We could have done it over here or whatever, and the argument would work just the same. So we shrink the interval. At stage n, we make sure to exclude R sub n. Maybe it was already excluded for the reason that you were describing, in which case, great, we don't have to do anything. I mean, we should, but if Rn was inside, that's exactly when we need to shrink to avoid it, right? And then the point is that any nested sequence of closed intervals will have some real number inside all of them, and that real number will therefore be different from all the Rn's, because all the Rn's were systematically excluded, but the real number Z that's inside all the intervals was never excluded. So therefore it can't be equal to any of the Rn's, and that's the contradiction.
So can we just pick any A and B and the proof will work from there?
Exactly, yeah.
Okay, thanks.
Okay, any other question? Oh, I see. So someone says the nested interval seems really similar to the proof of Bolzano-Weierstrass. So I think that's right. So I guess Cantor was first, though, right? Because this is what is the date? I don't know the date. 1880 something. I don't know exactly when Bolzano-Weierstrass was proved. So, okay. Any other questions?
I have a historical question, if you
Sure.
will. It's about ordinal multiplication and why we denote it the way we denote it. So x plus x, if we were talking about polynomials, most people would write it as 2x instead of x2. So of course there was a choice to be made since ordinal multiplication is not commutative. Do you know why this odd choice was made to have?
Well,
the
so,
two?
right, it's in Cantor's writings. Cantor did it this way, and he defined alpha times beta means beta copies of alpha. And I mean, you can criticize that, you know, because of this 2x thing, and it causes confusion. So sometimes people come into set theory and they mix it up. I've even seen extremely famous mathematicians, you know, write their ordinals in the wrong way. So it goes against this competing convention that you're talking about. But one answer to that is that this Cantor notation is extremely old. I mean, it's, you know, 100 and almost 100, more than 120 years old, 140 years old. Alpha times beta means beta many copies of alpha, according to Cantor. And if you look at Cantor's book on the transfinite, the notation is completely contemporary. Almost all of that notation has survived to this day, and it's readable, which is not true of many other mathematical writings. Often when they're that old, the notation changes over the years to something else. And so Cantor's notation was really very good, and a lot of it carried on. So I think the particular detail about this non-commutativity thing is with Cantor. He defined it that way. So of course, it also makes sense. I think this is how you define, say, the product of partial orders or the product of relations. If I have two orders, say P and Q, then I want to do P times Q. And what that means, according to Cantor, is Q copies of P. Yeah, and you can use that, say, on the lexical order and so on. So it's not just about ordinals, but any two orders. They don't even have to be linear orders and so on. And this idea about you have two structures A and B, and you form A times B, meaning B many copies of A, and that sometimes is not the same thing, even isomorphic, to A many copies of B. And so I think it's pretty standard that when you're defining this kind of generalized abstract product, that you take A times B to mean B many copies of A. And it's due to Cantor, I believe. All right, any other questions? So in that case, I guess we'll close, and thank you all for coming, and I hope to see you next week. The topic is geometry. So see you all next week.